Assalamu alaikum. We will start the lecture by recalling some points. So, said before in the start of this lecture, four relations that R is a relation on a set S, which is partial order on the set S if R is reflexive, antisymmetric, and transitive. And these are the three things. That's how we check that how a relation is reflexive, antisymmetric, and transitive. Then we have a set with a partial order is called a poset. And then a partially ordered set is linearly ordered set or a chain if for all x comma y, x is less than or equal to y, and y or y is less than or equal to x. Then we have learned that let we have a poset, and then a comma b is a subset of this S set S. Then C is inside S is an upper bound of the set if A is less than or equal to C and B is less than or equal to C. And we call C a lower bound of the set A comma B if C is less than or equal to A and C is less than or equal to B. Similarly, an element D inside the set S is least upper bound LUB of A and B if this A is less than or equal to D and C is less than or equal to D. So D should be a upper bound again. And if C is inside S is an upper bound of the set, then D should also be less than or equal to C. Then we will call D a least upper bound. Again, an element D is a greatest lower bound GLB of the set A comma B, which is a subset of S, if D is less than or equal to A and D is less than or equal to B. So D is a least upper bound, lower bound. And if for some C inside S, which is a lower bound of the set, C should also be less than or equal to D. So differentiate with the conditions that over here, D is less than or equal to C and D is least upper bound. Here, C is less than or equal to D and D is greatest lower bound. Then we have notations. So we denote least upper bound of the set A comma B in this poset by this symbol, and we denote the greatest lower bound of this set in this poset by this symbol. So this we usually called OR, and this we usually called AND. These are the names of these symbols. Then we have also discussed a Zone's lemma, which says that if every chain in a poset has an upper bound in the set S, then S contains a maximal element. Then we have discussed a poset is a lattice if it has what? A greatest lower bound and a least upper bound in L for all A comma B inside L. And we have get a bunch of examples. We have discussed some properties of the lattice. We have also discussed how a lattice will satisfy these properties, and then how a lattice can be a modular lattice. So a lattice is called modular lattice if for all elements A, B, C inside L, A is less than or equal to C implies that we have this property to satisfy by these three elements inside L, for all the elements inside L. And then we have a distributive lattice if it satisfies the distributive property with these two operations, OR and AND. Then there are some other properties for the distributive lattice. And now we will talk about the examples. So example 1, I should make it more. Example 1 is, now suppose that in a poset, which poset? Say P is a set and it has order, is a partial order on that. We have A and B, B and C, and the property A and B and C exist. Where A, B, C are in this P. What we need to do, we show that A and B and C also exist along with A and B and C, they are both equal. Let's try to show that. So solution. Now we have A and B and C, which is given in the problem, and they are less than A. A and B and C is also less than B and C, where B and C is less than B. Less than B, and B and C is less than C also. Hence, A and B and C is a lower bound of A comma B. Why? Because since A and B exist, we find that A and B and C is less than A and B. Remember this sign and this sign, they both are similar. So this should be some property for this poset, and we are trying to say here the same property we should be proving. Okay, then we have, hence we have A and B and C is the lower bound. The lower bound of what? The lower bound of A and B comma C. Now late, there is some D, which is a lower bound of this set. Then D is less than or equal to A and B. Sorry, D is less than or equal to B and C, not A and B. Yeah, A and B, because the first element A and B. and it is also less than or equal to C. Thus, D is less than or equal to A, D is less than or equal to B, and D is less than or equal to C. Thus, now since B and C exist, we have D less than or equal to B and C. Also, A and B and C also exist. Hence, D is less than or equal to A and B and C. Thus, A and B and C is a greatest lower bound of A and B, comma C. Consequently, A and B and C exist, and A and B and C is A and B and C. I guess they both have the same upper bound, so they are equal. Number two, we'll show something very special about a distributive lattice. So show that every chain is a distributive lattice. Remember that when we say and talk about a chain, then we have said something about the chain previously by the context of Zone's lemma. Every chain is a poset. If every chain is a poset, in a poset has upper bound in S, then S contains a maximal element. And then we have discussed the lattices. So over here, when we say that every chain is a distributive lattice, we have few things to consider. So let's start the solution. Remember, a distributive lattice is a lattice which satisfy the distributive property using and or operations. So let's take a lattice or a chain. Let's say this L, this poset is be a chain, and A, B, C we take from this L. Now, since L is a chain, either A is less than B or B is less than A. And if A is less than B, then A or B is B, and A and B is A with this condition. And if B is less than A, then A or B is A, comma, A and B is B. Hence, for any two elements A, comma, B in this chain, A and B and A or B exist in L. Now we have two cases. The first one is that A is less than B, and the other one is B is less than A. We have these two cases, so we use these two cases. So suppose A is less than or equal to B, such that we have case one. In case one, we take B is less than or equal to C, and then we have now A and B or C is A and C, because B or C is C, and this will be equals to A, because with the property that A is less than or equal to B and B is less than or equal to C, A is less than or equal to C, and with that A and B is going to be A. And A and B or A and C is going to be A or A, which is again A. Hence, we have what? We have distributive property A and B or C is A and B or A and C, because this is A and this is A. Then we have case two. Case two says that, let's take A is less than or equal to C. Now, well, for the case two, we have another case. So let's say case two is C is less than or equal to B, but we have sub case. Let's say sub case, which we name it 2A. In that, we assume A is less than or equal to C. Then, in this case, we have A is less than or equal to C, where C is less than or equal to B. Now, A and B and C, or C is A and B, which is A, because we have already defined that C is less than or equal to B, and so B or C is going to be B, and then we have already defined that A is less than or equal to C, so A and B is going to be A. Then we have, or and we can say, A and B or A and C is what? So the first one is A, or the second one is A, so we have A. Hence, A and B or C is A and B or A and C. Very cool. Then we have a subcase 2B. In that we assume C is less than or equal to A. In this case, we have C is less than or equal to A and A is less than or equal to B. Now, A and B or C is A and B, which is A. And A and B or A and C is A or C, which is A. Hence, A and B or C is A and B or A and C. Similarly, if B is less than or equal to A, then A and B or C is going to be A and B or A and C. Hence, a chain, every chain is a distributive lattice. Perfect. Number 3, and the final one, says that prove that a lattice with the partial order is modular if and only if A and B for all A and C is A and B or A and C for all A, B, C inside L. Solution. Now suppose this lattice is modular. So there should be a property which it should satisfy. That property is, we will use A and B for all A and C can be written as A and C for all A and B by commutativity, then we can say A and C for all B and C, sorry, A by the commutative on this bracket only. Then we can also say that A and C for all B and A, and this property is by modularity. Because since A and C is less than or equal to A, then we just have to write A and B or A and C. And hence we have proved that. The first part. Now we will show the converse. Now conversely, we suppose that A and B or A and C is A and B for all B or A and C for all A, B, C, and L. And we will show that with this property, a lattice will be a modular lattice. So let A, B, C in L be such that A and A is less than or equal to C, then A and C is A. Now C and B for all C and A is C and B for all A and C. Hence, C and B is for or A is C and B for all A, i.e. A or B and C is A or B and C. And this is the complete proof. Thank you so much. In the next lecture, we will talk about functions. One function, onto function, how a function is well defined. And then we will talk about some properties. We will talk about the composition of functions. And then we will talk about also about the invertible functions. See you in the next lecture.